We're going to continue with what we were talking about on cross-bound swirl on the last video and extend the idea a little bit as well. So I want to talk about multiple zeros. When we see a polynomial like we have written here, y equals x plus 2 squared times x minus 3 squared, we talked earlier about this idea of degree, that the degree of the polynomial is the same as the exponent on the highest power of x, and that we can tell what it would be on something like the polynomial we see here if we imagine, without actually multiplying it out, that x plus 2 squared will give us one term that has an x squared in it, and the x minus 3 cubed, when we multiply it out, will have a term that has an x to the third in it. And when those two highest powers of x multiply each other, we'll end up getting an x to the fifth, which means this is going to be a fifth degree polynomial. Now, we also talked about this idea of zeros, and we're going to kind of delve into that a little bit more. We said we can find zeros when we take our polynomial, factor it, and this has already been factored for us, set it equal to 0, and solve. So when we solve this, the x plus 2 squared is going to give us negative 2 as 1, 0, and the x minus 3 cubed is going to give us positive 3 as another 0. So we will say these are two, we will call them distinct zeros, meaning that those are two different numbers that make the polynomial equal to 0. But we want to introduce another idea, a new idea perhaps, of what's called multiplicity. And so this is the idea of a number that makes this polynomial equal to 0 more than once. So the culmination of this chapter that we're on, we're going to talk about what's known as the fundamental theorem of algebra. And the fundamental theorem of algebra will say that the degree of the polynomial will exactly equal the number of zeros of our polynomial if we allow imaginaries, and also if we agree to this idea of multiplicity. That is, that a number could be a 0 more than once. So this idea of multiplicity is because of this factor of x plus 2 squared, in a sense, this means we have our polynomial is x plus 2 times x plus 2, and then the x minus 3 cubed is, we can think of it as being x minus 3 times itself 3 times. And so it would be reasonable to say that what we have is negative 2 is a 0 twice, or we would say with multiplicity 2, and that x equals 3 is a 0 3 times, that is with multiplicity 3. And if we agree to this, then the 2 plus 3 is 5. That's going to agree with what we're going to say from our fundamental theorem of calculus, is that this has 5 zeros. It just happens that 2 of them are negative 2, and the other 3 are going to be positive 3. So that's the idea, as this new idea of multiplicity. Now, let's just for practice and to review what we did last time, let's graph this and use our cross-bound swirl rules. So I'm going to put our xy axis in here. We said that we're going to have one x-intercept, 1, 0 at negative 2, and we're going to have another one at positive 3. We talked about end behavior, which we can think of formally as what's the limit as x goes to negative infinity of this polynomial. And so if we put in a very large negative number into the x plus 2 squared, once it gets squared, it's always going to be positive. When we plug a large negative into the x minus 3, so a large negative minus 3 cubed is going to be negative, and that product is going to be negative. And so this is going to go to negative infinity, or that is, it's going to drop and go down to the far left. So our left-hand behavior is going to be negative. When we approach the negative 2, since that came from the x plus 2 squared, it's going to bounce. And when we come back to the x equals 3, since that's to an odd power greater than 1, it's going to swirl, and that's what our graph is going to look like. Okay, let's do another example here. And let me get that out of the way. So for this one, we're going to add another twist to it, or something we talked about earlier, and combine it with what we just talked about more recently. That is, we're going to take a polynomial, we're going to factor it to get into the form that we want, find the x-intercepts, and then look at the end behavior, and then use our cross bounce and swirl rules. So to do this, we're going to have some pretty strong factoring skills here. So the first one we're going to look at is going to have a particular technique that we're going to have to use to factor this. And you can see we have 4 terms, and it's got a cubic. It's a third-degree polynomial, so we can't factor this using our standard factor a quadratic techniques, the box and diamond, or however you do it. So what we're going to do here is called factor by grouping. So we're going to pair up the first 2 terms and pair up the second 2 terms, and then try to pull out the greatest common factor just for those 2 terms. So if we factor an x squared out of the x cubed plus 2x squared, that will leave behind an x plus 2. The greatest common factor for the next 2 terms is going to be a negative 4, and that also is going to leave an x plus 2. At this point in time, you'll know if this factor by grouping is the correct strategy or not. If these x plus 2s, these things in the parentheses, are identical, then we can go forward, and this was a good choice. And if those aren't the same, then either we made a mistake or factoring by grouping is not the right strategy. So now we're going to pull out those x plus 2's, that common factor of x plus 2. That will leave behind the x squared and the minus 4. Now that x squared minus 4 is the difference of 2 squares, so we can factor that further into another x plus 2 and an x minus 2. We'll write this, because we're going to use our cross-bound swirl rules in a moment here to graph it, so we'll write that as x plus 2 quantity squared times x minus 2. Now we can take this form and we can graph it. We can see from our factored form that we're going to get an x-intercept at negative 2, and that we're also going to get an x-intercept at positive 2, and so I'll put points down there. Looking at our left end behavior, if we, and I'm going to write this again using this formal limit as x goes to negative infinity of our, I'm going to just call it f of x. Then if we put in a large negative, when it gets squared, this will be, the term here is going to be a positive, but the large negative will make the x minus 2 into a negative, and the positive times negative is going to be a negative. So that's going to go to negative infinity or go down. So our graph is going to go down to the far left. As we approach the negative 2, that came from the x plus 2 squared, so an even power is going to make it bounce. And when we come to the x minus 2, that's to the first power, so it'll just cross. So there we have factored and graphed. Let's look at another example, a little different kind of factoring issue here. So we're still going to do the same thing. We're going to factor it and graph it, but this is going to be x to the 4th minus 5x squared plus 4. This is known as a quadratic form, and this calls for a little different strategy in trying to factor it. So because you have 3 terms, think like it sort of looks like x squared minus 5x plus 4, and you might think of factoring that using your box and diamond, which would be exactly the strategy we're going to use here. But instead of the first terms being x and x, we're going to get x squared. And we're going to get, we'll end up with a minus 4 and a minus 1. And you can see that that will that will, when you multiply that out, you're going to get an x to the fourth from that term, and you'll get a minus x squared and also a minus 4x squared, which will combine to give us the minus 4x squared and a positive 4 for the third term. Now we can factor more because both the x squared minus 4 and the x squared minus 1 are difference of two squares, so each of those can be factored further into an x minus 2x plus 2 and an x minus 1 and an x plus 1. Now it's in factored form. We factored it completely. Now we're ready to go to the graph, and we can see where the x-intercepts are going to be. And we're going to get a positive 2, a negative 2, a positive 1, and a negative 1. So there's going to be the negative 2, the negative 1, the positive 1, and the positive 2 that are the x-intercepts. As we look at that far left behavior, the limit as x goes to negative infinity of our polynomial, we're going to see that if we plug a large negative in, all four of these will be negative, and when we multiply the four negatives, it's going to then go to negative infinity. So, it's going to go to positive infinity, so it's going to actually go up to the far left. So that means it's going to look something like this. Now these are all to the first power, so we're going to cross, 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 and our graph looks something like a big W. Okay, I'm going to go to a new screen and talk about a different kind of problem. We're going to talk about can we find an equation of a polynomial with some given characteristics. Find an equation of a polynomial, and then I'm going to say with, and I'm going to give you some conditions. We're going to do three different problems here, three different examples. They're all going to give you sort of similar information, but maybe in a little different form. And so I don't want you to get confused by the form or the vocabulary in which it's given. So first we're going to find an equation of a polynomial, and I'm going to tell you that polynomial has zeros, 2, negative 2, and positive 1. And then I'm also going to tell you that it has a y-intercept of negative 8. So in this equation, what we know, or what we need to know, is what we started talking about last time. If we have zeros, we have also factors. So if 2 is a 0, that means that our polynomial is going to have x minus 2 as a factor. If negative 2 is a 0, then x plus 2 will be a factor. And likewise, if 1 is a 0, then x minus 1 is going to be a factor. Now, this is really a whole family of polynomials. So anything that has these factors as part of its decomposition is going to have those zeros, but it could have any constant in front and still satisfy that property that is going to have those three zeros. So that might be a 1, that a could be a 1, it could be a 5, it could be a negative 2, so on. To narrow it down, we're going to use our information about the y-intercept being negative 8. That's telling us another value of x and a value of y that go together. That's saying that when x is 0, y is negative 8. So we are going to plug the negative 8 in for the y and the 0 in for the x's, and that will allow us to solve and find out what the a is. So I'm going to say negative 8 is equal to the a that I don't know yet, but we're going to find, and then 0 minus 2 times 0 plus 2 times 0 minus 1. So that's going to give us negative 8 is equal to, and then we're going to still have our a, and that's going to be then a negative 2 times a positive 2 times a negative 1. And so we've got negative 8 is going to be negative 2 times 2 is negative 4 times another negative 1 is going to be 4a. And that's going to tell us then that a must be negative 2. And that tells us then that I'll stick with the p of x. The p of x is going to be, the a is negative 2 times x minus 2 times x plus 2 times x minus 1. Most of the time, I'm not going to ask you to multiply that out, and so we'll just stop right there and call that our answer. So let's look at a second problem similar to this, but I'm going to give you the information a little bit differently. So we're still asking the question, find an equation of a polynomial that has these characteristics. And this time I'm going to say what we have is f of negative 3 is equal to 0, and f of 1 is equal to 0, and f of 4 is equal to 0, and f of 2, we're going to be told, is equal to 5. So when we go to solve this, this information right here is equivalent to what we were told up here about zeros. The negative 3 is a value of x that makes the function equal to 0, so it would be correct to say that negative 3 is a 0. And a big thing we're trying to say is if we know a 0, that tells us that we must have x plus 3 as a factor. Similarly, if 1 is a 0, then x minus 1 is a factor, and if 4 is a 0, then x minus 4 is a factor. Now, this 2 does not make the polynomial equal to 0, so that's not a 0. That's not going to give us a factor, but it will tell us a point that's not on the x-axis, which is going to allow us to solve for that a. And so here we can see that that is the same thing as saying when x is 2, y is 5. So we will say 5 will equal a times, and I'm going to plug the 2 in where we see these x's. And then we'll come back and we'll solve this for a. So that's going to tell us that 5 is equal to a times the 2 plus 3 is 5, the 2 minus 1 is 1, the 2 minus 4 is negative 2, and so that's going to tell us that 5 is equal to 5 times 1 times negative 2 is a negative 10a, and so a is going to be a negative 1/2. And that makes our function f of x equals, the a is 1/2, and then we still have the factored form of our polynomial, x plus 3, x minus 1, and an x minus 4. And again, we're not going to multiply that out. We'll just stop right there and call that good. Let me do one more example for you here, still in the same vein as the one we've been doing. We're going to still find a polynomial that has, and I'm going to say this time it's got x-intercepts, and I'll say the x-intercepts are a negative 1/2, a positive 2, and a negative 2, and I'm going to add some more conditions here. We're going to say that the polynomial has integer coefficients. Let me try that again. Integer coefficients. And I'm going to ask you to write it in the form y equals ax to the third plus bx squared plus cx plus d. That is, we're not going to leave it in factored form. We're going to multiply it out. So let's talk a moment about what this integer coefficients means. If you recall, an integer is something that is not a fraction or a decimal. So examples of integers are 0, 1, 2, 3, 4, negative 1, negative 2, negative 3, and so on. So when we start like we have before by saying if negative 1/2 is going to be a 0 or an x-intercept, if it's an x-intercept, then negative 1/2 is also a 0, and x plus 1/2 is going to be a factor. Now, I'm going to have to come back to that because we're going to have to get integer coefficients, and right now that's going to possibly goof that up. So when we look at this, if I multiply this all out, this 1/2 is going to multiply some of these other x's, and they're going to end up giving me a polynomial that has coefficients that are not integers. So I can fix that early on by, instead of calling that x plus a half, I can call that 2x plus 1, because negative a half will still make this a 0, so that's still going to give us an x-intercept of negative a half, but it won't give me fractions in our as coefficients in our polynomial once we multiply this out. Now, I didn't have any other consideration for what that leading coefficient might be, so I'm just going to leave that, what might be an a, I'm just going to leave that as a 1 and just see what this gives us. So now we're going to have to multiply it out because we're trying to put it in this form that is not factored. So these three factors are all multiplying each other. It doesn't make any difference which order we multiply them in, so I think it's going to work out easier if we multiply the second two first, because if we notice x minus 2 times x plus 2 will give us the difference of two squares, which is x squared minus 4. That is going to simplify things a little bit. And so now when I multiply this out, we're going to get a 2x cubed. So there's our x cubed term. We're going to get an x squared. We will get minus 8x, and we'll also get a minus 4. And that is our polynomial with integer coefficients that has x-intercepts negative a half, 2, and negative 2, and is in the form that we were directed. All right, very good. This is a start.